So how many of you can remember the first time you felt joy from programming? Raise your hands. I knew you wrote Ruby here. For me, that came when I was 12. I was talking to a friend about how we'd just upgraded our family PC to DOS 5. That was a big deal. And he said, "Oh, DOS 5, you've got Quick Basic. I have to teach you." I said, "What's a Quick Basic?" He said, no. We weren't actually at a computer at the time. So he got out a piece of paper, and he wrote out print, and he told me what it does. Unconvinced, I said, so what? There are lots of ways to put text on a screen. I don't even need my fancy EGA graphics card to do that. And then he showed me if-then and explained how conditionals work. And a light bulb went off in my head. And in that moment, my social life died. But I fell in love with code. And that's a love that's persevered even through almost a decade in management. But I have learned that one of the best ways to tarnish something you love doing is to take money for it. And as professionals, it's easy to get into a rut. It can feel like, man, I just write the same input validation and the same database CRUD day in and day out. And what used to feel like sorcery can start to feel pretty rote. But for me, when I write an AI that solves a problem I couldn't have solved myself, maybe in a way that I would never have thought of myself, I feel some of that old spark. And writing a genetic algorithm can be a great way to rekindle joy for your craft if you can just figure out what they are. So you hear genetic algorithms, some of you might think, cool. And you think of scenes from The Matrix, or you hear the theme song from Super Metroid. And others will think, man, that sounds really hard. Genetics, that's like protein folding and cellular biology, Human Genome Project, that really bad semester of OChem. But it's really not that hard. Now, definitions like this one don't really help. There are a lot of $5 words here. It's not that bad. We can break it down. Stochastic here just means random. Heuristics are simple rules you use to make decisions every day. A rule of thumb, or, it's raining, so I'm going to stay off of I-35 on my way home. Combinatorial optimization might be a little harder to get your head around, but it's just a class of problems to which the answer means you have to combine items from discrete sets in a particular way. So what this really means is that genetic algorithms are a fancy method of trial and error. They're really powerful. If you think about just life, the stuff of biological evolution, it's the one thing in the universe that actively fights against the laws of thermodynamics. It's a big deal. It's why we're all here. It's a good tool to know, but it's not very accessible, or at least the literature isn't. There are some good tutorials for the easy end of the genetic algorithm spectrum. The advanced stuff is justifiably pretty complicated, but there's a lot of room in the middle where I don't think you need a PhD to understand it, but you do need to know it to really put these in practice. So I'm hoping that I can talk through some of this intermediate stuff today, and you'll leave here able to actually use this. So genetic algorithms are they're used broadly across industries, typically only by quants and academics, but operations research, so any kind of manufacturing or value chain optimization, applications in financial trading algorithms. They grew out of a field called the study of complex adaptive systems. They're excellent at timetabling problems, scheduling problems. If you need to design a network topology, this is a good class of algorithms to pull from. So to explain what they are, I'll explain how they work. For a given problem, you create what's called a population of solutions at random. You go through those, you score them, you have some way to put a number to fitness, what makes one solution better than another. And then from mostly the best of that population, you mix and match, put the parts together in a new way, and you get hopefully better solutions. And you repeat that process until you find one that you think is good enough. A little bit of terminology to get out of the way. Now, for everything we'll talk about today and most of the genetic algorithms you might encounter in the wild, they work on a data structure that is one-dimensional. So it's an array, it's a list, a vector, a string, whatever you want to call it. In GA speak, it's a chromosome. So you might also hear it called a genotype or an organism, but it means it's a solution. And along that vector, each position is called a locus. And the combination of some value and a position is called an allele, just like in DNA. And one other bit of terminology that you probably know, but to keep me honest on not making any of this too difficult, is a function landscape, or if you're working in GAs, a fitness landscape. So you might have seen something like this if you've ever dabbled with any machine learning. I'm sure you've seen it, where along the x-axis you have possible solutions, and the y-axis is that fitness score, or utility, cost, whatever the terminology that you're working in would call it. This is a univariate problem that's really easy. Usually they'll be multidimensional. I tried really hard to not put much in the way of code on slides. I thought visuals might help more, but if you want some code, I published some. I won't attest to its quality, but you're welcome to check that out. Follow along or look at it later. And we'll explore genetic algorithms through a couple of problems. The first of those is the knapsack problem. To set this up, I like to imagine that we're in a dystopian future. The machines are programming themselves. Programmers are now outside of Jevons paradox. We can no longer count on good salaries or free snacks, and we resort to a life of crime to make ends meet for our families. And we find ourselves having just broken into a warehouse, probably Dr. Wiley's, and we can only carry but so much stuff out with us, and we want to make sure that we maximize the value of what we take with us. Maybe that's value is dollars, maybe it's bitcoins, maybe it's calories, whatever. So we say we can only carry, in this case, 15 pounds. How do we maximize what we're taking out? The first step in designing a genetic algorithm is figuring out your encoding scheme. That's the data structure that you'll use to represent your problem, bring something out from the problem space into the GA space. And here, because it's easy to fit on a slide, we'll say we have 8 different items. We want to find the best arrangement of those. So we'll use what's called binary encoding. So we'll take a binary string. Each bit represents one of those items. If the bit's on, the item is in the knapsack. If the bit's off, it is not. So here's just a very random contrived solution. It's invalid, unfortunately. So now we know how we'll encode things. We have to figure out how will we create more of those solutions. The one I just showed you, we just alternated every other. That's not very useful. So you probably think, well, we'll just scan through left to right, and with some probability, we'll say it's either on or it's off. Maybe it's 50%, maybe it's 30%. But that's probably going to leave us with an invalid solution. So at some point, we'll max out the weight. And so where we were targeting 15 pounds, now we're at 20, 25 or something. And a lot of our solutions might be invalid. So we could score those out, but how you handle an invalid solution is a really important design decision. It's usually best to just not create them in the first place, and then if they arise later, you score them out. But if you don't handle it now, you'll waste a lot of clock cycles. So instead of doing that, you might think, well, I'll just track how heavy each solution is as I generate it, and when I hit that limit, I'll stop turning anything on. And that's not so good either, because it's going to be skewed to the left. Now, this is a binary string, so you might say, I'll just pick a random number, and you're going to have a similar problem, but it'll be skewed to the right. So instead, you want to make sure that as you go through this list of items, you do it randomly. You might still track the weight. Don't generate anything that's invalid. But this way, you're guaranteed to not skew one way or the other, so long as you have a good random number generator. So now we have an encoding scheme. We have our initial population. We'll talk about how do we compare two solutions. And this problem, this was my first pass. There's some problems with it, but I'm going to own up to those mistakes for your benefit so that you can learn from them. So I said, okay, well, we want to maximize the value and we want to maximize the weight up to our limit. So, okay, that's pretty easy. And the first time I ran that, I got solutions where maybe one was 14 pounds but $20, and one was 15 pounds but $15, and the one that weighed more but was worth less would win out. Well, that's not so good. So, well, maybe we should just add some kind of bias, weight the value more. That still gets a little wonky. And if you step back, you say, well, I don't really care how much it weighs. I care what it's worth. So we'll make value binary. We'll make weight binary. We'll try to maximize value. And that gives us a fitness function of 1 minus 1 over x, because originally I had wanted to combine the two things in an aggregate function. This is okay. So as value, which is x, increases, the fitness, y, is still increasing, but maybe not proportionate. So instead, maybe we'll just make it really simple and say the score is the value. I overthought this. I'm sorry. Learn from what I did. So why does this matter? Well, the next step in building a GA is to pick your method of selection. There are two kinds that I want to talk about. The first, and the most common by far, is called proportionate selection. So in this case, your GA is going through, you iterate over each generation, and you will go through the entire population and assess your fitness score. So we've scored everything, and now we will run a Darwinian lottery in which things with the higher scores will get more lottery tickets. So we'll pick a random number somewhere between 1 and the sum of all the value scores, but the higher the value score, the more likely a solution is to be selected. And that's an attempt to mimic that Darwinian selection that you see in nature. Like I said, this is the most common selection method for a GA. It gives you the most direct path to convergence, meaning it will take fewer iterations through your algorithm because you never miss a really fit solution. You're looking at the whole population. It also gives you a feature called elitism when you say, well, I want to take the best X%, probably just 1 or 2, from my population, and I will protect it. I'll say it will never die. It will always be available to the pool to continue through crossover. The alternative, or at least the one that's worth explaining in this presentation, is called tournament selection. And here we take a sample from our generation, and we only score those that we pick, and then we always take the one with the highest score from that sample. So while this might take a few extra iterations to converge, it does have the advantage that it doesn't run the fitness function nearly as much. So if your fitness function is really expensive, you might consider using tournament selection. Also, if you find you're having scaling problems, tournament selection gives you kind of built-in scaling because it doesn't care about relative distance so much. And now that we have a way to select the most fit members of any population, we have to figure out, well, how do we recombine them? And the most natural way is called single point crossover. This works just like crossover in humans, where you get half your genes from your father, half your genes from your mother. From one solution, you take half. From the other solution, you take the other half. Stitch things together. Pretty straightforward. Now, genomes in nature are really long, really complex stuff. most of our problems are not going to rival the human genome for complexity. So as an alternative, we might use what's called uniform crossover, where we just pull from either parent at 50% probability. And this can actually converge faster for simple problems. So if I run this, you can see, well, they both produce solutions that are just as fit. The population goes up in fitness much faster with uniform crossover, so we're converging faster. In this case, you could run fewer iterations to feel good about having got the best solution. And anytime you're looking to compare two different GAs, the things you want to look at, most importantly, the total fitness, or whatever the best fitness from your population is. You might look at clock time to converge, or how many iterations does it take. Occasionally, number of solutions explored, or other measures like how much of each parent continued on, but that's getting a little academic. What you really want is the best solution in the smallest amount of time. So crossover is exploitive. It takes the best solutions and uses that territory we've already visited, builds on that. Mutation is exploratory. So it lets us explore new permutations of solutions. And in nature, the most common type of mutation is actually inversion, where part of a chromosome comes off and gets reattached, but the wrong way. That was experimented with early on in the history of GAs, but it really didn't help. And so you'll usually use what's called point mutation if you're working with binary or value encoding. So you'll just have this, introduce a random transcription error where you'll change one bit. So if you put it all together, truth be told, when you only have 8 items, it doesn't make for a very interesting slide if you're watching things grow. Your solution would look like this. But if you want to see how this comes together in maybe a more tangible way, you can check out that repository that I put up and run this with like 100 or 200 items and watch the output, and you'll see things change a lot more. So I said I wanted to teach some of the intermediate space for genetic algorithms, and I just ran through the basic stuff. I'm sorry. I felt like I needed to provide some foundation. A more intermediate problem might be a seating chart. So about this time last year, my group was moving into a new space, a different building, and the engineers and the data scientists, well, they work best when their conditions are quiet, but we had a team of pre-sales people and consultants who spent a lot of time on the phone, and so we wanted to try to separate those two. We had a lot of other requirements. It was a pretty complicated fitness function, and we still ended up debating its merit and changing the output a little bit. But here's a sample. We'll keep it simple. So you might have a roster like this. You got a bunch of engineers, maybe a couple of managers, and some salespeople. How do we want to represent that? What kind of data structure might we use? We'll reach for what's called permutation encoding. So in this type of encoding, our data structure is a list, and it always has the same items in it, but where those items occur is meaningful. So in this case, each locus, each index in our data structure represents a seat, and the values we put in it represent a person. And I've color-coded them by roles. So when I was working on this last year, I went out for a run, and I was really bothered because I didn't like my vectorization scheme. I thought it was, well, this is really naive. And what I didn't like about it is that it didn't preserve the locality of the space we were working in. So the distance between locus 0 and 3, the distance between locus 0 and 4, in Euclidean space is just 1, but in vector space, it's 4. And I didn't like that. So I thought, man, if only there was a way to vectorize something and preserve the locality of my problem space. And I thought, oh yeah, Well, that would be a Hilbert curve. If you're not familiar, this is exactly what Hilbert curves do. So they take your vector and bend it so that you have a better representation of a two-dimensional space. And to illustrate why that's better, so the locus or the vector index is the x-axis in these charts, and how far away they are from the origin, 0, 0, is the y-axis. Sawtoothing here is bad. So you can see, okay, the Hilbert encoding, that does look a little bit better. Does it matter? Well, it does help. So I think I ran this for 30 iterations, not a lot. You can see in the early iterations, the Hilbert strategy worked a lot better, so that's good. Now I only ran this comparison once, so that means it's worth further investigation, but it's not definitive. So with the encoding scheme behind us, we can figure out how to create those example solutions. It's pretty easy in permutation encoding. Since you have a list of items, you just shuffle the list. Make sure you shuffle a copy. You don't want to shuffle the reference. Our fitness function gets a little more complicated, though. So remember, we said we want to keep like groups together. That matters. Well, engineers should be close to engineers so they can work on problems together. Same with salespeople. Probably in practice doesn't matter with managers, but whatever. So we'll go through and we'll tally up all of the edges within each of those sets. We'll say, well, the distance there, the total distance, that'll be part of our score. The other part of our score is repulsive. We said, well, you know, salespeople, they're loud. We want to keep the engineers away from the salespeople. And so we'll do the same thing, but here we're going across sets. And we'll say, okay, we'll subtract the repulsive score from the attractive score, and you know, we have a score of 18. When I ran this the first time, my results looked like garbage. What did I do wrong? And anytime you have a GA that's failing to progress, it's almost always related to your fitness function. And here, I just made the mistake of selection worked on more fit individuals with higher scores, and here the lower score is better, so I just had to invert them. And the fitness function looks kind of like this. I didn't show the whole thing. You get it. To do that inversion, I figured out what's a theoretical max. I might have been able to do something more fancy if I'd given it a little more time. And now we'll come to crossover. Permutation encoding, there are probably 5 different types of crossover that are worth knowing. I'll talk about 2. The first is ordered crossover. It's pretty straightforward to implement. You take half of the first parent, and then you scan through the second parent, and for each value that isn't present so far, you move it down in order. And so this is good because it it preserves the relative order of your problem. But that's not so good in a seating chart when we care about the absolute position that each value's in, where each person is sitting. So instead, we might try partially matched crossover. So here, you take a random section from one parent, and then for each value that it displaces in the first parent, you match it up. It's kind of hard to talk through, but you can see the visuals. And then you just take whatever's left from the first parent. So again, it's always good to compare these things sometimes, even though what sounds like it might make sense doesn't work. In this case, the first few iterations did a lot better using PMX or partially matched crossover. And the last design choice we have to make is how do we mutate? And in permutation encoding, you can't just pick a random locus and change its value, because then you'll have two members of your set of values. You have to keep them distinct. So instead, you just pick two spots and swap them at random. So to see how that works, I took the best member from each generation and put it up on the slide. You can see how things kind of change. Now, we started off with a pretty good solution, and over the course of a couple of iterations, it shuffled things around, so managers are neutral, the salespeople are up in a corner, and the engineers are all kind of clustered together with a little bit of a buffer space. So not too bad. Now, on a 4x4 grid, that's pretty easy to figure out. You could do this with some linear programming. You could work it out on pencil and with pencil and paper if you wanted to. But when you expand your seating chart out to 10, 15, 20 seats wide, then it gets a little more interesting. So I'll go through a couple of other types of problems more quickly. I want to make sure that I leave you with all the things that you might need to put these in practice. There's another variant of the knapsack problem called the unbounded knapsack. So instead of our fixed set of items, we have a fixed set of classes of items. We can take as many as we want. Same setup, and it would work the same way, same fitness score, etc., but our encoding is different. You can represent it with what's called list encoding, and so you have values. Your values are each item, and instead of a fixed width vector, you just have a variable width list. You use a single point crossover that's modified just slightly so that it picks from different positions in each of those two chromosomes and puts things back together. Traveling salesman problem, pretty well studied. GA isn't the first tool to reach for, but it's not a bad one. So in this problem, if you're not familiar, you want to minimize the total travel distance to hit all of these different destinations. To solve this with a genetic algorithm, I would use permutation encoding, where each city is a value, and then the order between cities is what you're selecting on. You can use ordered crossover, or something that I just couldn't figure out how to fit on a slide called edge recombination. A little more advanced, but it does perform better. And then the same proportionate selection and swap mutation we already talked about. And finally, the nurse scheduling problem. So I'm guessing that here you've encountered this in some form. So scheduling problems are great territory for genetic algorithms. The setup is, well, you have to always have a certain number of nurses scheduled. You can't schedule a nurse who's got approved PTO. You can't schedule a nurse more than 2 consecutive shifts. I know this happens, but I personally don't want somebody who's been working 16 hours to be handing me my meds. You ought to give them a break in between shifts, and you ought to respect shift preferences. This problem is harder than what we've talked about so far because you have both hard and soft constraints. So you could say, here's our sample schedule. And you already know everything you need to know to be able to solve this. The real trick of it is in the encoding. And to solve it, it's the same crossover and selection. It's binary encoding, but the way a scheduling problem is normally solved is to build your constraints, at least the hard ones, into your encoding. So here, wherever Grace was on the schedule, we've got each locus represents a possible day and shift. And anyone who is on PTO, you just remove those from the encoding. And that way you'll never schedule somebody who could not be scheduled. And that eliminates some of the invalid solutions up front. So we've talked a bit about how to use a genetic algorithm. I want to talk a little bit more about when you should use them. They're a great tool, kind of a heavy tool. They work really well when you may not have an exact solution to your problem. If you're going to use a genetic algorithm, make sure you don't need an exact solution because it may not get you one. It's a heuristic. It'll give you something approximately the best, but maybe not the absolute best. They work really well when you have a very large search space. That is perhaps their biggest advantage. They parallelize well. They can be distributed relatively easy. Not that any distributed problem is easy, but within the sphere of optimization problems, they distribute well. They work very well on complex fitness landscapes. So if you have a concave or a convex landscape, you probably just want to use something simple like hill climbing. But if your fitness landscape looks more like a pincushion, then something fancier like a genetic algorithm is the way to go. Or if you're trying to find a Pareto optimal solution. So we'll talk about how these stack up to a couple of optimization algorithms. The first is simulated annealing. Is anybody familiar with, okay, so I know optimization really doesn't get a lot of attention in 4-year CS programs, but simulated annealing is another heuristic, kind of similar in that it just tries stuff more or less at random. Not quite random, but basically. It's a really good combinatorial optimization tool. It works pretty well for, well, what might be big problems to you. It tends to find solutions faster. A GA will find a better solution, but it's going to take more time. They really work pretty much the same way under the hood. The difference is that the GA is the more parallelized version. You can think of simulated annealing as a genetic algorithm with a population of 1. Also, if you take the time to learn genetic algorithms, you can take them to more problems than you could simulated annealing. So while they might not be the best tool, at least you can learn one tool and get more mileage out of it. Another common optimization algorithm is branch and bound. This is probably the first thing you ought to reach for if you're working on solving a seating chart. It guarantees the best solution, but it only works on relatively small problems. And when problems start to get bigger, people start to make hacks to branch and bound. So then you lose your best solution guarantee, and now, well, why not just use a genetic algorithm? When I talk about GAs, people usually say, oh, well, why wouldn't you use gradient descent for that? It's kind of the darling of the machine learning world. It's used all over the place, at least today. Gradient descent is really for continuous optimization, not discrete optimization. Now you can use either of these algorithms in either space. You can hack either one. Gradient descent won't handle quite the complexity of a GA. Again, a GA, you can just throw more and more threads at it. And in a genetic algorithm, your function does not have to be differentiated. You don't really have to know anything about calculus. That might be a big plus to some of you. It is to me. And when you're talking about things that are inspired by natural stuff, okay, genetics, yes. But what about neural networks? And this is probably the one that comes up the most. They do very different things. So a neural network is used primarily for classification. Yes, they can write music videos and screenplays now, but they are mostly for pattern recognition. And a genetic algorithm, while it can be used for classification, there's a whole branch of study called genetics-based machine learning. They're really primarily used for optimization. So if you're interested, if you want to know more about the space, Richard Dawkins is a great author to turn to learn more about genetics. And if you want to learn more about genetic algorithms, ironically, the literature is a little incestuous. John Holland was the researcher who really built the field. He wrote a few good books. John Koza wrote the books on genetic programming. He was a student of John Holland's. And David Goldberg wrote what is probably the best field guide kind of book. Now, it's almost 30 years old, but I've read almost the whole thing, and it's all still relevant. There have been new additions to this space, but nothing that really invalidates what was written there. And Goldberg was also a student of Holland's. So, the next time you find yourself stumped with a hard optimization problem, remember that life finds a way, and think about using a genetic algorithm for it. Thanks. You guys have questions?
Hi. I'm a bit new to all this, so I was curious if you could explain the difference between discrete and continuous optimization.
Yeah, so discrete optimization, you could think of it as working in integers. So you're trying to pick values like 1, 2, 3, 4. Continuous, meaning you're picking a real number, 1, 1.1, 1.11, 1.111, etc.
Hey, thanks, Jeremy. It seems to me that the encoding is probably less important than the actual fitness function. Is that a correct assumption?
Encoding is the most important thing to get right the first time because it's the hardest thing to change.
Is that because of performance reasons, or because it seems like the fitness function is really what changes the output or the output of the results?
The fitness function will be the most important thing to performance, but if your encoding is wrong, then all of the code you write around it will have to change, or you'll end up writing some wonky abstractions where you really don't want abstraction. But getting the fitness function right is probably the harder thing, and if you screw that up, then yeah.
I mean, in your opinion, based on your experience, is that the most difficult aspect of genetic algorithms, is actually finding the right fitness function?
Yeah, there are a lot of important design choices along the way, but I'd say the fitness function is the hardest.
Hi. It's pretty much in continuation to the question that he asked about the fitness function. Does it ever happen that you kind of have a local, like the best optimization locally, but it's not like the globally it's not the best optimization?
Yeah.
So how do you deal with that then?
That's kind of the curse of optimization, especially if you're working with heuristics, where you don't know for sure that the solution you've picked is the global optima.
Mm-hmm.
Your choice of algorithm helps a lot there. That's one of the drawbacks to, obviously if you're familiar with hill climbing, basic hill climbing is only good for finding the locally best solution. Simulated annealing does better because it has that temperature, which is a lot like mutation in a genetic algorithm, where it can look at a bigger part of the search space. Mm-hmm. And so it can jump out of the neighborhood that it's currently focused in, and it might find a better neighborhood elsewhere and move around. A genetic algorithm is within the algorithms I talked about, and probably anything I'm aware of, it'll have the best chance of finding the global optima just because it can visit so many solutions. Does that make sense?
So is it like you have like a lot of results which are optimally the best, and then you are actually kind of comparing with those if you need more, if you need to actually modify the heuristic itself or something else?
Yeah, and I kind of glossed over how you know when your algorithm is done. The simple thing to do is say, well, we'll just run it for, 5, 50, 500 iterations, whatever kind of works. You might instead say, well, if the best score from a generation hasn't improved in so many generations, you might say, once we hit a score at a certain level, then we'll exit the algorithm.
Okay, thanks.
You're welcome.
Hi. What makes it so that you can't encode such as a seating chart problem in a two-dimensional array rather than just the one-dimensional vector with all the twists and turns?
Well, you could use a two-dimensional data structure, and then you'll have to write your own custom crossover or recombination and mutation. So you could, and there are if you ever read the O'Reilly book, what is it? I think something about AI for game design or something like that. They have an example of a genetic algorithm that works on it's a Java or C++ class, and then they had to go and figure out how to recombine things and how to mutate things on their own. You could do that, but I think you might. I would be a little reluctant. There's a lot of good research on crossover on one-dimensional structures or tree structures. That's maybe a little more advanced. But when you start to work on 2 or 3-dimensional structures, you're getting outside of what's been studied. And I think you would find that there are traps and it's not as easy as it sounds at first. I might be wrong, though. There's a gentleman here who's had a question for a couple rounds, I know.
I was wondering, is there any way you can combine algorithms? So, like, kind of like machine learning to see, okay, this gene, or I guess this locus has like significance. So this is maybe where we should start like doing the most variation, whereas these ones don't really matter. Is there
Yeah.
a way you can combine those?
You're thinking of like a PCA or something on values or alleles or values at a locus?
Yeah, I'm just thinking like more like applying like, okay, so this one really changes my result and has impact for like the utility that I'm trying to measure, whereas these ones don't really affect anything, so I can kind of rule them out for like, you know what I mean?
Yeah, you could. If you're building a GA that's going to run all the time, for instance, in the Postgres optimizer, if it can't find a good execution plan pretty quickly, it flips into a genetic algorithm. In that kind of situation, it might be worth doing that kind of analysis on your fitness function to understand, well, this particular allele or gene is really important to my fitness function, and so maybe I want to change how I handle selection or crossover around that or mutation. You'd want to incorporate that back into your fitness function. It's not often done. Usually the fitness function design is going to account for that. Now, you asked about combining algorithms, and it is pretty common to say, well, for instance, I mentioned gradient descent, and genetic algorithms kind of compete with gradient descent in the training of neural networks. Sometimes a GA will be better to weight the inputs. Sometimes gradient descent will be. Another common thing is because a genetic algorithm is really good at finding the globally best neighborhood, but not really efficient at finding the absolute best solution in a neighborhood, you might run a GA for a while and then drop out into hill climbing. So that'd be another way to combine.
So I had some experience about 10 years ago using a genetic algorithm for one of my projects. And one of my biggest frustration was that it had so many different options, different knobs, different ways to arrive to solution. And I liked in your talk that when you were trying different approaches, you were looking at graphics. So my question is, do you know of any current kind of meta-optimizations for genetic algorithms? I know there were some research articles, but are there any practical solutions that allow you to kind of automatically explore this large field of options?
Yeah, I'm trying to think. If you connect with me on Twitter, I read a lot of papers before giving this talk. I've used these a couple times, but I wanted to, know more than what I did know. I think I came across one. Generally, though, the approach, I think one of the reasons why GAs tend to be used mostly by quants and academics, people with an operations research background or PhD, is because the way to do it today is just to know the breadth of the space and to pick the right options based on an almost expert knowledge. One of the reasons why I thought this might be a good subject for a talk. If you dig into any class of algorithms, I think you'll find they're all pretty big. You know, like you say, well, I know neural networks because I went through one example and I had one layer and I used backpropagation. I know everything there is to know, and that's just a tiny little slice. Just like, if you have something that just runs through binary encoding and single point crossover in a GA, that's just a tiny little slice of the space. And that's why data scientists are so hard to find.
Hi. I was wondering if there's an equivalent to a set of design patterns for this topic, or is it just kind of tinkering with different options?
Well, that's a good question. I kind of hoped that I would show some just by going through this is how you would solve a couple of different problems. I haven't really found much of that in the space other than in Goldberg's textbook that I mentioned. Probably not organized as design patterns, or at least not with that nomenclature. I think it could be better. The patterns are really more types of crossover, types of encoding, types of mutation. Might be an opportunity though.
Hi. So this is a clarifying question. It looked like that the crossover was between two members of each generation, and that produced one new member. So does that mean each generation is half the size as the previous? And
No.
Is that what terminates the computation?
No, sorry, that was unclear. So sometimes when you're looking through papers or texts, you'll see crossover explained as taking two parents and producing two children. You can do it that way. Or you can take two parents and produce one child. Or you can take three parents and produce n children. But you normally fix a population size. So you say, I want to maintain a population of 10 or 100 or 1,000 different solutions. And every time I build the next generation, I fill it. So I'll always create that many children.
Another quick question here. So assuming you have a very, very large search space, will you typically then take lots of different samples of the population of that entire search space and run it through your algorithms and understand if they converge on a similar, quote, answer? Is that, or do you just take one population out of the very large search space?
So if I understand, I think you're asking, is it better to have a uniform sample or maybe to sample neighborhoods and run multiple algorithms?
I'm kind of drawn on my understanding of in the machine learning space where you might have like a billion things that you're looking at, but you don't have the computational resources to exhaustively train a model on those billion things. So you might take 100,000. So, but you would take lots of different sample sets out of that billion and then run it through to train a model and see if they produce an optimal result. So do you do a very similar thing in the GA space?
Yeah, I think you'd want to, if your problem space, it depends on the size of your problem space relative to the size of the population that you have the computational power for. And you'd want to start by trying to sample your search space uniformly and see how that works. And from there, I don't think you would necessarily run through like PCA or SVD or something to try and figure out what features of solutions are the most important. Again, that kind of goes back to the earlier question, and you probably want that to bake out in your fitness function. But you might find that you're better to have multiple populations running in parallel. If you're distributing a GA, you'd have like different populations on each node that then periodically have to compete against each other. And that might be the better way to handle a really large search space.
Unfortunately, we've run out of time, but just give a round of applause for Jeremy. Thank you for taking your time to do this presentation.
Thanks for having me.